Ciao Diego.
Ciao, buongiorno. Good morning.
Great, Diego, we can hear you well. We'll do a test later as well before the next session, but if we can hear you, it's then all good.
Okay.
Okay. So. Patrick?
Yep.
What do you think we start?
Yeah, maybe we can.
Is everyone, well, I hope some people are here.
Yeah.
Some other are maybe connected on the YouTube. I'm not sure. I hope.
We can wait 3 minutes.
Yes, sure.
Yep.
Hi Patrick.
Hi Stefano.
Perfect.
Yeah.
Right.
Yeah.
Ciao Gianni.
Ciao a tutti. Hello, everybody.
Hi Gianni.
Hi.
Well, Patrick, I think
Yep.
we can maybe start.
We can start.
30
we are
people
30,
here.
yes. There are 30 people in line. Okay, we can start. Hello, everybody. I want to thank you all being present this morning, even remotely, for the start of this workshop. I'm particularly pleased to open this workshop today. Our choice was to combine the fourth workshop of the EVE project. And the EVE project is coordinated by Joan Marty. And the final workshop of the LAVA project, which is coordinated by Andrew Harris. In both cases, for the two workshops, the main objective is to establish a link between the civil protection, the different state, and the scientist. And also in both cases, the workshop was to focus on the crisis related to effusive eruption. These two congresses were to be held in Reunion Island. It was therefore quite logical to group them together in order to have a wider impact and a wider audience. The circumstance that you all know make it impossible for us to meet in La Réunion, unfortunately. I'm sure you regret this, especially considering that Piton La Fournaise is erupted 3 days ago. I will stop here. I will give immediately the floor to the first three speakers. We have three speakers this morning at the beginning: Andrew Harris, Joan Marti, and Alessandro Tattadini. Before we can hope for a short break. To the speaker, please respect your time. And to the audience, please put your microphone and your camera off during the presentation. But at the end of the presentation, it's better if you put your microphone and camera on to ask a question. It's more friendly to see you on the screen, even if it's on the screen. So, Andy, the word is to you.
Thank you, Patrick. Thank you very much. And I too would like to extend my welcome to one and all at last to this workshop. It's version 3. We've cancelled the real one. We've reset up a virtual run, cancelled that one, and now set another one up, which we finally are very happy to be at. We've persisted in persevering because we have around us here in this room such a unique group of experience in effusive crisis response and monitoring. And it's such a wonderful opportunity to get everyone together to share experience and above all to implement a group exercise to check or qualify our monitoring communication protocols and see how we can improve our ability to communicate during crisis. I'd like to introduce you to and thank the 2 organizing committees. The first list there were those who organized the workshop itself: Auriel, Aline, Nicolas, and Patrick. Above all, Auriel's put in an enormous amount of work to making this happen. As I've said, she's organized it, unorganized it, organized it, unorganized, and finally organized it one final time to be here today. So thank you, stacks, Auriel. The second group there is the group who's organized the series of exercises. There'll be a first exercise that's an expert elicitation that's been put together by Alessandro, Aline, Andrea, and Willie. And we'll be saying more about that later this morning. And on the last day, we'll also be implementing a Eurovolc exercise, some questionnaires that Lara Sandri's put together to assess the efficacy, if you like, of the exercise and the material we'll be distributing. Before we begin, I'd just like to say a few words about ANR Lava and what we're about. ANR Lava was a research project funded by the French National Research Agency in 2017 to research the problem of lava advance into vulnerable areas, specifically populated areas, but also vegetated areas. We began in 2017, January 2017, and with the COVID extension, we'll be closing the project out next month in 2021. It's involved about €500,000, 6 students, many of which I see here today. Hi, guys. And 3 postdocs and 3 institutes, the Laboratory of Magmas and Volcan, the Mathematics Institute at the University of Grenoble, Pierre Saramito, who'll be speaking this afternoon, and the Observatory on Piton de la Fournaise. And our main goal has been to come up with an effusive crisis response protocol, above all focused on Piton de la Fournaise and the needs of the observatory there. And the driving force is that we've been funded by Challenge 9 of the ANR, and that is to secure the liberty of Europe and its citizens and residents, which with Brexit doesn't include me anymore. So the roadmap for the research was as follows: 3 blocks. The first block was to make measurements to allow us to better clothe the models, if you like, to better make the source terms and link them. Primarily, we were interested in looking at the effects of trees on the mechanics and dynamics of the lava flow, better initialize the rheological models that drive the lava flow simulations, better define the source terms due to textural effects, mainly vesicularity and crystallinity, and examine the effects of changing topography on the flow paths, and above all, the key source term, lava discharge rate. Once we'd done all that, which began in January 2017 and took up the first 2 years of the project, we then began slightly in parallel to begin to update the models, where we took the Flogo model, Oriel recoded that and upgraded it to make it PyFlogo, written in Python and now freely available from computers and geosciences, and merged it with Massimiliano Favali's downflow to allow us to become stochastic in terms of the number of flow paths we modeled. And then we began to apply that for a response protocol that involved the generation of real-time hazard maps that Oriel will talk about this afternoon, and also make probabilistic risk assessments. And the final step, the exclamation mark here today, the 12th of April, was to run a community workshop and launch a community exercise to examine how we work together during unrest and examine how effective our response reporting is when we report within groups, so within scientific groups, within civil protection groups, and between the two groups, so between civil protection and science and protection monitoring, and science monitoring and civil protection. So the protocol that we've solidified is this. I've already presented this at a previous EVE meeting, so I'll go through it relatively quickly. The observatory is the mouthpiece. They trigger the alert level. So once an eruption watch is declared, Morova and Asta are targeted so that they, at first detection of a hotspot, can give us discharge rates to initialize the lava flow models down here. At the same time, the observatory issues the vent coordinates that allows us to launch the flow paths in downflow, and then using the discharge rates to estimate how far down each flow path the flow will likely advance, to then produce flow runout maps, flow line maps, and flow length maps, which go into the reporting area, which then goes into the observatory. This is a communication entirely within the scientific part. Nothing is released beyond the observatory. It's for the observatory to then release the maps onwards to the wider population. The beta version of all this was launched 1 month after the project began in February 2017 with that February eruption on Piton de la Fournaise. And it really was a 3-step and 3-map model. The first thing we'd do would be to run the stochastic map to get the array of likely flow paths and the line of steepest descent. The line of steepest descent would be sent from INGV Pisa to LMV, where we'd run that in Flogo to estimate the distance and velocities that the flow was likely to reach. So these lines here, this first line here, the red line, is the velocity and distance that we'll obtain with a time average discharge rate of 4.2 cubic meters per second. So at that discharge rate, we've got a run out of about 1.2 kilometers. For the 8.7 cubic meters per second, we've got about 1.8 kilometers. And that was then driven by Morova from the University of Turin. They would send, or Diego would send, the range of discharge rates, which is what we have here. This date, this is for the 18th of February, just here, and his range of discharge rates is 4.2 to 8.7, and all of that together equals the report, which was sent as an email to Arlene, the directrice of the observatory on Piton de la Fournaise, in this format here, basically a list of the likely lengths for the the discharge rates that the system is giving us. That was rather cumbersome. So over the last 5 years, largely driven by Oriel's hard work, we've come up with this. This is the only thing that's sent out now. It's in yellow, all the likely lava flow paths that we believe the current flow will cover. The red is the line of steepest descent. And with the arrows here, that's the length that we believe the flow will extend given a discharge rate, so from 10 cubic meters per second to 55 cubic meters per second. This is actually the live one. This is for today. This was the eruption that began on Friday, and this is the simulation of Saturday. It's been projected onto a base map that Civil Protection and La Réunion requested, because this is the map they're used to looking at, and it's showing all the issues they are concerned with, that being one, the belt road here, linking the south of the island to the north of the island, will that be cut? Vegetation on the caldera margins here, will that be touched by the lava, thereby causing forest fire problems? So do fire crews need to be deployed? And here for the observatory are all the monitoring stations. So do we need to helicopter in to evacuate a GPS or seismic station in a flow path? We put this into action on Friday, and I just thought I'd go through the timeline for that as to how things happened. And these are at times, Central European times, that an email was received by the group. So at 13:28, Arlene declared alert level 1, eruption watch, due to seismic events and deformation patterns. And about 4 hours later, she issued eruption level 2, eruption imminent. In fact, just 6 minutes later, the eruption onset was confirmed from the camera at Piton Bert. There we have the event opening on the southwest side of the Dolomieu cone, feeding a lava off to the right of this image. So based on that and the approximate event coordinates apparent in this image, Oriel configured and issued the first map. At 18:38, the event location was confirmed, and we confirmed the map, and the first diffusion rate from a ground-based check was confirmed at 3.8 cubic meters per second. So the flows, according to our prediction, should, with current conditions, remain quite close to the vent. Early the next morning, European time, the vent coordinates were updated from helicopter by Nicola, and the map was updated and reissued. And at that point, Arlene sent it to the La Réunion Civil Protection for use there. And at 9:28 in the morning, the first Morova hotspot was sent with a caveat that cloud cover was making it not possible to have a good, accurate effusion rate estimate. It was probably greater than 1 cubic meter per second. So that's what went on over the weekend. Now we're here on Monday, and what I'd like to consider now or review now is the exercise that we'd really enjoy carrying out with you during the week. And the exercise will be an expert elicitation that we've tuned to be useful and accessible for both civil protection players and scientific players and monitoring players. And what we want to do is fulfill two needs. One, to fulfill the need of Eve, and that is to generate some probabilistic data for a period of unrest or a phase of unrest at Piton de la Fournaise. But a second thing we want to do is to assess the efficacy of the reporting system, primarily how observatory reports and data, graphics given therein, interpreted and used by people who read and use those reports, primarily the scientists and the civil protection actors. So part one of the exercise will be this morning, where later in a couple of talks' time, Alessandro will introduce in further detail the test. And then there'll be a day and a half of training. That's to say, all of the talks are aimed at giving you as much information as possible to understand how to interpret unrest at Piton de la Fournaise, the monitoring system and the response system. So then in part two, we will launch the exercise. So that'll be Tuesday afternoon, and it'll be an event assessment where you'll be given observatory reports, and we'll be asking you the questions, the basic questions that we need. What do you think is going to happen? Where do you think it's going to happen? And when do you think it's going to happen, based on the information you've been given? In part three, which will be Thursday, so on the Wednesday, we'll analyze all of the data, and we'll present the data back to the group and debrief with a discussion of the results. and launch part 4, which will basically be an appraisal of the exercise and the material, the data format and the presentation format, using Lara Sandri's Eurovoc questionnaire. And we'll explore that further on Thursday afternoon. So that's the roadmap for the exercise part, but for the exchanging of expertise and experience part, this is the general layout of the next 4 days. So today we're going to focus on unrest and response in France, but with a very special focus on Piton de la Fournaise and effusive crises there. Tomorrow in the morning, we'll move to more of a societal focus on Piton de la Fournaise. We'll actually begin that this afternoon because one of our speakers can't make it tomorrow. That's Carolina Rizzo. She'll be talking this afternoon of the use of social media in crisis response, and we'll continue that tomorrow morning. Then in the afternoon, we'll move to a final training session, which Patrick will lead, going through a few unrest examples at Piton de la Fournaise, and then we'll launch the exercise together. Days 3 and 4, Wednesday and Thursday, we'll then explore experiences of unrest and response during effusive crises elsewhere. And I think we've got a pretty comprehensive list of most centers that have recently experienced diffusive unrest, that being Hawaii, Democratic Republic Congo, Kathala, Galapagos, Etna, and Iceland. And on day 4, we'll close out with an open floor discussion, the exercise debrief, and a little discussion on perspectives for the future, where to go from here. So with that, I'll hand over to Juan to welcome everyone on behalf of the EVE partner of this workshop.
Okay, Harry, thanks. Good morning to everybody. I'm going to talk briefly about the EVE project, which is the second project we are going to discuss about during these 4 days. And EVE is basically addressed to the development of the first early warning system for volcanoes in Europe. And it's mainly addressing the problem of unrest and how we can understand unrest and how we can provide the information in time for being prepared about the next eruption. This is something that we started working on several years ago with a previous project that was called B-Tools, in which we developed several software packages that were mainly organized in a kind of systematic methodology to address the study of unrest and to provide with scenarios, the most probable scenarios for what could be the potential future eruption. In this second project, both projects have been funded by the European Civil Protection Office inside the European Commission framework programs. But this second one is mainly addressed to the last part of this methodology, which is the development of this early warning system. So basically, I think I suppose I have to share is it, okay. I suppose you see my screen, is it?
Yes, yes, all good.
Okay.
Okay. So, well, this is the project in which there are several groups. There are really 6 groups in European groups. Our group in Barcelona, which now has changed the name. Now it's Geosciences Barcelona. It's not this name anymore. Then the University of Iceland, CNRS from France, Observatorio Vesuviano from Italy, faculty from University of Lisbon in Portugal, and the University of Clermont-Auvergne in France, who are now organizing this meeting. First of all, before explaining about this project, I want to thank the organizers of the meeting, and in particular Aurelio, for all the work you have done, because it's in this situation it's really difficult to organize this kind of meetings, and I understand that there is behind a lot of work to be done when you have to prepare this online meeting. So thanks a lot to all of you for this good. I'm sure this is going to be a very good meeting. Okay, so the idea is very simple. So this is just a diagram which shows the idea of what is behind an unrest episode. We have the background level of any volcano, which is different. If we compare between one volcano with another, we will observe that each volcano has its own background level. But if we know the volcano and we have the monitoring, just controlling what is the activity, the current activity of the volcano at any moment, we can see if there is any deviation from this background level. So we can say if there is an increase in this activity, we can start thinking that maybe an eruption is possible. When we change from possible to probable, so we are more sure about what is going to happen, it's when we should declare the alert for this potential eruption. Of course, this will increase, the activity will increase and we change into a state which is could be designed or called as highly probable. For we are pretty sure about the eruption is going to occur. Then we are sure, fully sure, and we have the event at the end. So all this process that goes from what starts to deviate from the background level to the final event is what we understand as unrest. What we should do at that time is when the volcano starts to be at unrest, the local volcano observatory should start communicating. Of course, if they are they think that the eruption is probable, they should start communicating to the European Civil Protection. This is our idea, and the other European civil protections about what may happen. Because basically the reason for this warning is because ash in the atmosphere. This is basically the main hazard that could affect other countries in addition to the proper country that has the volcano on its territory. But at the same time, this European Civil Protection, what it does is just it helps to the other European Civil Protections in case what happens is too much for being managed by themselves. So the civil protection is just organizing the help, what is needed when anything that happens in a certain country or a certain place extends the capabilities of the proper country or the proper region. So this is why I think it's important to communicate, to create this, or to generate this early warning system, just to communicate with the European Civil Protection and then to other European countries about the possibility of having an eruption that may cause, in some cases, may put ash into the atmosphere, affecting the civil aviation and other, but also in case that the eruption could exceed the capabilities of the own country, so there will be need for additional help, for external help. So when the volcano enters into unrest, the local observatory should communicate this situation, and immediately this local observatory should start undertaking a short-term hazard assessment based on the long-term hazard assessment that is supposed they have done on this particular volcano. And this
Joan, please. Just a moment. We are just able to see your first slide on the screen.
The first slide?
Yeah. And we didn't see the others. Maybe it's...
You are only seeing this one?
The first one. Just the title.
Okay, I don't know what happens because in theory, I'm sharing
your screen.
I'm going back.
Yeah, it changed now. It's okay.
See it now?
Yeah.
Okay.
We have the second one.
We will keep this format.
Yeah.
And okay. So this is the one I was using to explain what should be the early warning, or at which moment it should be applied and why.
Thank you.
And this was the diagram I was using to explain this by definition of unrest. Okay. So at the moment this is applied and civil protection reacts on this, they should apply the protocols for managing this volcanic crisis. That in many times it will be sufficient with what is done in each country, but sometimes it will need the contribution of the other countries and the European civil protection to manage this situation. Okay, so basically this is the EVE project. So it's as I said, it's funded by the European Commission, and these are the group's participants. This is the web page. Okay, so where you have all the information about the project. And the idea, as I said, it's well, about the project. This is a project of a little bit more of 700,000 euros. And it was originally for 2 years, but it has been extended due to this pandemic problem. It has been extended for 1 year more, so it will end by the end of this year in 2021. And these are the groups I mentioned before that participate in this project. The motivation is very simple. All of you know about what happened in 2010 with that eruption in Iceland that affected Europe well, mainly because the interference with the civil aviation, but all the problems it caused and so on. So this is why I think an early warning system, or we think an early warning system is needed for this at European level. But basically it's just to connect the local observatories with the civil protection, European civil protection, and from the European civil protection to connect with the other civil protections in the rest of European countries. So just to organize the coordination just in time, well before the adoption starts. How it works is, well, what I explained before. So we have the groups or the groups of the science and the data that should be recorded for each particular volcano. This should allow to develop the short-term hazard assessment. And after that, we have the most likely scenarios that could occur for this particular eruption. So this is communicated to the civil protections, and then they should react according to the needs that will require this particular eruption, and the needs that each country will require depending on how much, or how they can manage for that particular eruption. So if they need help, they will have to, they should ask for help. If not, they can manage by themselves the problem. This idea is based on the previous project, but that was the Beatles project, in which we developed this set of tools, and all this is based on a systematic methodology to conduct long-term and short-term hazard assessment. The tools we develop are basically address spatial analysis, temporal analysis, simulation models of different kind of hazards and associated hazards. Then we have cost-benefit analysis, vulnerability analysis, also evaluation of the risk coefficient for each volcano. It also contains several communication protocols in which we just provide some guidelines on how to communicate this information to the different parts of the society. I mean, just the general population, but also media, also scientists, also managers. So anyone who forms part of this society that could be affected by this volcanic eruption. And the new module you have to incorporate here is just a volcano early warning system, which is the one we are developing in this new project. All this is controlled or was included in what we call the VolcanBox platform, which is a multi-platform that works with Mac, Linux, and Windows. And it's very simple. All the tools, everything we just include here is really very simple. We are not here depending on supercomputers and very complicated simulation models. All is relatively simple, probabilistic, and just to give an idea about what may happen before the problem starts to appear. So this is for an example of the results we can generate. So susceptibility map telling us about the probabilities of hosting new events, which is an important aspect we need to know before an eruption starts, where it's going to appear, which hazards can derive from this eruption. We can then elaborate particular maps for single maps for each particular hazard. Then we can combine them and obtaining a total hazard map that could be quantitative or qualitative, depending on the requirements and the needs in each case. So both can be obtained. When we have this long-term hazard assessment, then we can apply this to, in case we have a reactivation of the system, the volcanic system, and then applying or developing the short-term hazard assessment. This, for example, is a retrospective case we use for El Hierro. So when we had the El Hierro eruption about 10 years ago, we didn't have any hazard assessment for the island. So this exercise I'm showing you is something that we did after the eruption. And it was clear that if that was the information of susceptibility we had during we could have had before the eruption started, in this case, we saw that we had different places that could host new events. But when we combine this with the monitoring information, particularly the seismicity that was migrating south along the island, we saw that the probability of hosting a new event was changing with time until it was fixed in this point where the eruption occurred, 3 months after the unrest started. But if this information could have been available before the eruption started, probably our forecast would have been different to what it was at the moment we were working on this, because we could have seen that the eruption was going to be submarine. And in any case, during this particular unrest and crisis, and volcanic crisis, it was proposed that the eruption could be submarine. All people were thinking that the eruption had to occur on land, which was not the case finally. And this was because we didn't have this hazard assessment done before the eruption started, or before the unrest started, really. A real-time case, this is also other things you can do. You can, with this system, you can evaluate the variation, or you can make a forecast on all the different parameters you are controlling. Monitoring parameters, I mean, may change in the next report you are going to receive. So this is a probabilistic approach too. But for example, I can give you a real-time example in which and how the system works and has been working. In this particular case, it has been working quite well, nearly, I would say, perfectly well, which is the case of this last eruption in Iceland. This last eruption, I suppose that our colleagues from Iceland will explain about this with more detail. But just to give you a brief introduction on this is the susceptibility map we obtained just a few hours before the eruption started, which was indicating a red spot in this particular area. This was the lava flow model we simulated for that particular vent. That was a fissure vent in this particular case. And this is exactly where the eruption started. So exactly in the place we predicted. And this is how the eruption developed at the first minus hours, which is quite similar to what we predicted in this simple simulation model. So this means that applying the system to real case, at least in this particular case, it has been working quite well. We have other examples where this application, doing retrospective analysis, demonstrates that it works. So well, this is our contribution to this. Is the contribution of this project to the European Society for what concerns reduction of volcanic risk. What has been done till now in the project is well, here you have the different work packages that are included in the project. About management, as I said before, the the project has been extended for 1 year, so till 31st of December 2021. And we have already presented the three program reports, which are available at the web page. In terms of publicity, well, there is the website, which is updated regularly, including new information that arrive from different results or different things we are doing. We are preparing already dissemination activities. There are several papers already published with different aspects related to the project, directly related to this project. We have conducted the different meetings and workshops. Now we are in this conducting this workshop that had to be held in La Reunion, but due to this virus problem, we have to do online. But still, there are two more meetings, one in Naples that is planned for September. I don't know if these dates are still okay. And then a final meeting that sure will be held in Barcelona in December 13th to 16th in this year. We have also a database that in which data compilation is progressing day by day because we are receiving new information from the different partners. And with this information, we have started the short-term retrospective analysis of the different examples, examples of eruptions we selected to be studied in this project. So we have this eruption in Reykjanes, Stromboli, Etna, Pinar de la Fornés. Also, we have included Cotopaxi, from which we receive good information from our colleagues from Ecuador from 2018. And finally, we have this volcano early warning system platform. That is, this is the part which is still in preparation, in construction, because it will not end until the end of the project. And the things that are still pending, of course, are these Naples and final workshops. The Naples one needs to be decided if it's going to be in person or face-to-face, or will have to be online too. But the final one in Barcelona, we hope it will be just face-to-face in December. We have to complete the long-term hazard assessment for the case study volcanoes. We have by now only completed Teide, Vesuvius, Reykjanes, and Stromboli, Camp de Flegrei are still missing. And also we have to complete the new Volcan Box multi-platform, in which we are incorporating the different tools we developed separately in the previous project. So we have already incorporated into this new platform the spatial analysis and the temporal analysis and some simulation models, but the rest of things need to be implemented, and this is going to be done in the next month. And of course, we will have to prepare a final report for the project, and this is all what I can say that by now about IF project. Thank you very much.
Thank you, Joan. Thank you for this presentation. Now we have a presentation of the expert elicitation exercise by Alessandro. Alessandro, are you here?
Good morning, everybody. Can you hear me?
Maybe you can stop the sharing of your screen, Joan.
Yeah, but I think you should close it, did it?
I can close it.
I think so.
Ah.
Yeah, because you're not.
Maybe I will need the help of Oriel for that. I'm not an expert in Zoom.
Oh, me neither.
I'm trying, but I think I just got your video, Joan. Joan, I think you have a little button to the bottom of your screen that is called screen sharing, and there you'll be able to do it.
Yeah, but the problem is that now I cannot see the full screen.
Okay.
Now, okay, so
that is done.
Good.
Okay.
I do it. That's fine. Alessandro, I think you can do it now.
Yeah. Okay. Okay, can you see it?
Yes, perfect.
Okay. So, Okay, so good morning, everybody. I'm glad to be here. And as all the other speakers, I would really like to thank all the organizers of this workshop, and especially Andy, Julie, and Auriel for having invited me to help them in setting up this expert elicitation exercise with the big help of Andrea and Willy and Aline as well. So as Andy said at the beginning, with this very brief talk, I will just introduce you this exercise and very few details about the philosophy of the expert elicitation or structured expert judgment. I'll promise I'll be very quick, so then we can all go to have a coffee break. As I said, the first part of my talk will be just a brief overview on structured expert judgment with a couple of examples from my experience. And then in the very last slides, I will just give you some more details with respect to the schedule of this exercise and what we're gonna do in these days, in addition to what Andy has already said. So to begin, just to answer two questions that many people could ask. So why using expert judgment and what is expert judgment? So basically we can use these techniques which have been used by at least 20 years in cases like, for example, a real case with an effusive crisis. There's someone like the problem owner or stakeholder or civil protection authorities who needs to make a prompt decision, or in other cases that I will show you here, in case there's the need of doing a long-term planning concerning, for example, hazard assessment. And why using expert judgment? Because in these cases, there are no or very little data available. And for these reasons, the data are affected by a very high degree of uncertainties. And this uncertainty needs to be quantified in an objective way by merging the judgments of the experts in the area that needs to be pulled together with a structured methodology as the one done with the expert elicitation. So how basically is structured an expert judgment or elicitation? So basically, to summarize, there are three main steps in performing an expert elicitation. So first of all, it is important to choose the expert who needs to participate in this expert judgment. Normally, the minimum number is between 10 and 15 experts. The more expert you have, the more details you can add, but sometimes it doesn't really add that much more with respect to a core group of very highly selected experts. But it's true that choosing more experts is a way to select those experts who are best at judging the uncertainties. It is a critical point, and in fact, the analyst, the one who's running the exercise, should choose the expert all with a basic background on at least one aspect of the problem under investigation. And of course, it is important that the majority or the totality of the people have worked in study area or in similar situation. Although it is true that sometimes having an expert or two that is outside of the area of study, but with a clear basic background, could be useful because it could see things from a different perspective, and so add something that maybe people who have worked an entire life in an area doesn't see from that perspective. So once the expert have been chosen, then there's the step in which expert should be calibrated. And this is done through the proper questionnaire made by seed questions, which are questions in which expert performances in estimating uncertainty, and I would like to make it clear, which is not an evaluation of the degree of knowledge of the expert, but is more an assessment of their capability of correctly estimating uncertainty. So, and the performances of the expert are scored through two different scores, which are the calibration or the statistical accuracy and the informativeness score. The first one is basically the extent to which expert assessment match the statistical distribution of actual values. And the second one is how small is the uncertainty range that the expert provides. And then after the expert have been calibrated through this questionnaire, then there's the real questionnaire about the problem under investigation, which is the target questionnaire. In which the experts are asked to answer questions that really matters for the problem under investigation. To give you an idea how these questionnaires are made, basically in each questions you will see that there's for the seed questionnaire, for example, you will have a question about an actual value of something that is within the area of this the problem. And you will not have to give a single answer, but more you will have to give 3 different answers, which reflects the degree of uncertainty that you are giving to that particular question. And it is particularly helpful to see how this is made, because in this figure here in this slide, you can see that you will be asked to give 3 percentiles to each question: the 5th percentile, the 50th, and the 95th percentiles. These three answers will define an uncertainty distribution for each question, and basically the true, the actual value of that question should lie within this distribution that you are defining. So always keep in mind that the answer that you are giving will be basically the 50 percentile, which means that before and after your intermediate answer, there will be 50% in both sides. But after the 95th and the 5th percentile, there's a 5% chance of overshoot. So always keep in mind this distribution when you are providing the answer. And then the same format will be also for the target questionnaires. Of course, just a few words on the seed questions. You will see that they resemble, the seed questionnaire resemble the target questionnaire as closely as possible, but you will see also that there will be some a little bit outside problem questions, which are just warming up questions or very loosely related to the problem that we are investigating here, just to let you think more about the uncertainty estimation. And it is useful to think about the calibration and the information score as the sketch that you see here, that a high accuracy, a good calibration means that all of your questions are very close to the real answer. I'm talking, of course, about the seed questionnaires, and the accuracy is the degree of the dispersion of the uncertainty ranges that you are providing. So to give you an example from a real situation, to let you understand a bit more about the scores that you will be assigned. So here's a real case provided by Willy from one of these exercises, in which you can see that for a specific expert here, you will see like that here you have the realizations of the answer and the uncertainty range is provided by the expert. So you can see here that this expert is providing a lot of information, because it's providing a very narrow uncertainty ranges. But for most of the question, the true value has been not captured by the expert itself. And this leads to a very, very low statistical accuracy of this expert, but a very high informativeness. So in this case, this expert will we receive a very low weight due to the fact that the statistical accuracy or the calibration is very low. On the other side, this is another example of an expert which has captured for basically almost all the questions the true realization, but is providing a very low information because it's providing a very high uncertainty range. But in this case, of course, the statistical accuracy of this expert is much higher than the previous expert, but the informativeness score is lower. So what we are looking here is to have experts like this one, for example, in which we have a very, I would say, a good informativeness because the uncertainty ranges are not that big, but the statistical accuracy is much higher, and this is reflected on the scores that this expert has received. But in any case, keep in mind that in defining the weight that each expert will have at the end is more provided by the statistical accuracy, or in other way by the degree of the number of answers that have been captured by the expert. So my suggestion is that don't be too much overconfident in any questions that you want, and because here we are not assessing your knowledge, we're just assessing your capability of correctly estimating uncertainty. So very briefly, once you will have answered all the questions, then from our calculation, each of the experts we will participate in this exercise will be given a weight that is the result of these two scores, with a cutoff value that it helps in defining a better optimization of the joining of the pooling of all the expert answer. And the pooling of the expert answer will define a distribution for each target questions that is called the decision maker, which is basically the result of all the experts pulled together. And for this graph here, you can see that in this case, expert 1 has a weight of 12%, while expert 2, 88%, and therefore the decision maker, of course, more closely resemble the distribution provided by expert 2. So this is in general the idea behind an expert elicitation exercise. With these two slides, I would like just to give you two examples from my experience that many of you, of course, knows already. These are expert elicitation done for long-term projects, in which it's not like the one we are doing here, but it's just to give you the full overview of the capabilities of expert elicitation. So the first example that I'm showing you is referred to my PhD, in which the goal of the project was to develop a event opening probability map for Somma Vesuvius, in which we had to merge different maps related to different data sets that all concur to define the probability of having a vent opening within the Somma Vesuvius caldera, and we needed to define the uncertainty ranges for two parameters. The first one was the probability of having a vent opening inside and outside the caldera for the next eruption, because for these volcanoes, as you know, we all assume that vent opening would occur within the current caldera, but we wanted to assess if there would have been a probability for that. And the second thing is that we wanted to assign the weights to the different data sets in order that concurs to define this vent opening probability map. The result here is in this format, in which we have assessed with all the experts the weight to be assigned to each data set, which you can see in the diagram on the right. And so by merging all of the maps related to each data set with this probability distribution, we obtained a set of 3 maps, basically a min map and the 2 percentiles map, which describe in details the probability of having a vent opening within the caldera. And this, of course, does not mean that we have 3 maps, but more or less a continuous distribution of map between these three maps. And to give you an idea, in this exercise, we have 17 experts, 16 seed questions, and 15 target questions. The other example that I'm providing you that is still ongoing, which involved the tephra fallout probabilistic hazard study for Cotopaxi and Wawa Pichincha volcanoes. And for this expert elicitation, we wanted to assess the uncertainty ranges for 2 things. The future eruption type of occurrences at these 2 volcanoes in order to merge probabilistic maps from different eruption types, and the uncertainty range for the eruptive source parameters to be used in numerical models to develop probabilistic hazard maps. Here you can see an example for Cotopaxi volcano. Here is specifically the target questionnaire, basically the logic tree that each branch represents a target questions for the next eruption case at Cotopaxi. And in red, you can see here all the mean values for the probability distribution for each occurrence of both magma type and eruption type at Cotopaxi volcano. But for these mean values, of course, you need to think that, of course, in the questionnaire, we have elicited a triplet of values, as we will do here, the 5th, the 50th, and then 95th percentile. And the same thing here, you can see it for the case of the eruptive source parameters that we have elicited at this volcano. And again, here we have run this expert elicitation for 20 experts with 14 seed questions and a heavy duty target questionnaire with 55 target questions. So to jump to our exercise, I think that Andy has already given the backbone of the schedule. So I will just say that so today we just ask you to compile a demographic sheet, which you will find it on the chat at the very beginning of the chat of this Zoom conversation. In which you will be asked to provide your infos that will help us in define to have a better idea of the group. And once you compile this questionnaire, we kindly ask you to send it back to this address here, e.elicitation@gmail.com. And please note this address because you will have to send all the questionnaires at this address. For of course, this demographic sheet, but all the other questionnaire, please don't forget to write down your name and surname. And please rename your demographic sheet in this way. So demographic sheet, name and surname, .docx. So tomorrow afternoon, we will have at more or less 2 p.m., as already said, talk by Patrick, which will show us some arrest examples at Piton de la Fournaise that could help you in the questionnaires. Then you will have opportunity to answer the seed questionnaires. So we'll read all together the questions, and then you will have time to answer. And then we will do the same also for all the target questionnaires. Finally, on Thursday afternoon, you will have we will see all the results and we have time to discuss it. So few more details for the demographic sheet. You will see that there are 3 test questions at the end to assess each participant's perception on his or her probabilistic degree of certainty and uncertainty. For the seed question, you will have in total 18 questions, general question in general about effusive volcanism and specifically on Piton de la Fournaise effusive volcanism. you will have this questionnaire both in English and in French, and you will have the possibility to choose which language you prefer to answer. And this is the same also for the demographic sheet. You will have 45 to 50 minutes to answer. And please, in this case, don't Google the answer because, as I said, we are not assessing your knowledge. And if you're Googling the answer, of course, you could invalidate all the exercise. For the target questionnaire, it will be divided basically in 4 parts. So we'll have 4 questionnaire for 4 different phases, again, in English and in French. Each questionnaire will be preceded, we will read it together, a bulletin that has been kindly built by Aline with the same format as a real bulletin. But of course, this is an exercise. And you will have 15 to 20 minutes to answer each questionnaire, which is made, as Andy said, by 3 different questions. And apart from that, we will send you tomorrow also other materials that might help you in answering this question, which is a map of Réunion Island, the monitoring network, and the slope maps where are needed. So I think that's all. I'll stop here, and thank you very much for.
Thank you, Alessandro. We have time before to have a short coffee break for some questions. You can ask questions to the 3 speakers of this morning, and please put your camera and microphone on when you want to speak a question to one of the speakers.
Patrick, I will just start. Stefano Cioli had a question for you, Alessandro. If we are expected to fill it, the questionnaire, the spreadsheet tomorrow, today or tomorrow, before the exercise, or when do you want all of this?
You mean the demographic sheet?
Yes.
Yes, if you could please do it by today, at least by this evening, because we need to know the participant. Of course, this demographic sheet should be filled by those who would like to participate in the exercise, because we need to know how many people will participate.
Okay, thank you. Maybe I will send again all the information by email to everyone.
Yep.
And telling they must reply before this evening to be registered for the exercise tomorrow.
Okay.
Please ask your question directly. Connect and put your face with the camera. Anna, I will ask you a question. I see you put another question for you, Alessandro. So as you know, we have some people from the other side of the world, in Hawaii or Alaska and Ecuador. So if they cannot participate during the session tomorrow afternoon, is it possible to fill in the questionnaire offline, to do the exercise alone at home? Not during
for the target questions, yes, it's not a big deal. So you can do it offline if you want. But at least for the seed questions, I would say that it would be better if those who want to participate, at least for those questions, if you can do, we need to do it online, at least for that. But for the targets, it's fine. It's
maybe we'll do one exception for you, Hannah. You are in Alaska.
Yes.
If you have questions as well about the organization or the Eve or Aina, Lava, Andy and Joanne are still around for discussion. And then we have a short break before we start again in 20 minutes for the next talk.
Oriel?
Yes, go ahead.
I'll just share my screen for a second to look at the demographic sheet, just so that it's clear, because it's a very simple sheet to fill out.
Right. You want me to do that, or you're doing it, Andy?
I I've got it here somewhere.
Okay.
There it is. There. Okay. Is that good? Is that shared? So
Yes.
Okay.
so it's a pretty easy sheet to fill out. So it's just name and surname at top. It'll be in the end completely anonymous because we'll give everyone a code number. This is just to go to Alessandro on that private Gmail site, so no one else will see this. Your email, gender, age group, nationality, your type of position, country where you currently work, years of experience or relevant experience in the post currently held. And then there's a series of questions relating how you rate your expertise, how many volcanic crises have you been involved with, have you done an expert elicitation before, and what you believe your current rate of knowledge for Piton de la Fournaise is. Where this is a great group because we're going to have a full range of experts, from those at the observatory who are 100% through to those who have experience with crises and effusive crises, but not necessarily Piton de la Fournaise. And then there are the test questions in the final part, the 3 test questions that Alessandro wants to use to make an initial assessment of the expert's ability to guess. So that's the
So
form.
maybe we could just see together the 3 questions to see if they are clear. I think yes, but so basically, as you can see, these questions are just to translate from your qualitative perception of uncertainty to real values. So we will just ask you to provide your lowest and highest values of the level of certainty that you would need to provide the answer no to the question, will be there an eruption by tomorrow? So maybe, I don't know, it could be between 99 and 100 or 70 and 100, or it's up to you. It's just to see your perception. And the other 2 are basically made it as the same format.
But there is an eruption right now at Piton. How do we answer that?
No, but this is in general. So it's just that, yeah.
Here we have a question asking if PhD students are allowed to participate. And the idea was to make the participant of the workshop to participate and not to, I guess, to open to others, or if they are connected. I don't know, Andy, if you want to say something about.
I would say all are welcome, because we'd like the full range of experience and a full population of differing backgrounds, differing lengths of experience, different ranges of experience. So really, the more the merrier. And there are potentially six of us to do the coding, so we can probably deal with a maximum of, how many would you say, Alessandro, would be our limit? About 60?
Yeah, 50, yes, 50 to 60, yeah.
So yes, everyone's welcome to join in and play.
Okay. Stefano, Cioli, if you want to just put your camera on and ask your question. He wants better explanation on the questions.
Yes, okay. Well, I was wondering if you can explain again the meaning of these test questions. So when we are expected to fill in this, just now or during the exercise? And what what is the question in the 3 ABC?
No, so the street question, if you can just do it right now, these are just to see how the different participants think in terms of probability associated to answer yes or no. And it's just to see if for example, there are some differences in how people translate their their feeling about certainty and uncertainty to real numeric values. Because for someone, maybe to say there tomorrow there will be an eruption, I need to be 99% sure. While maybe other person could say, oh, for me there will be for sure an eruption if I am 80% sure.
Okay, I get. So it's to test for me what is the meaning of not, yes, or unsure.
Exactly. It's exactly. Mm-hmm.
I get it. Thank you.
Welcome.
It's Benjamin with a question.
Hi, everybody. Thanks
Hi,
for
Ben.
the talks. It was very interesting. I have a question for Alessandro. I've already done some elicitation with him on Cotopaxi and Wawa Pichincha. And I was wondering if your seed questions, your seed questionnaire, can help identifying some impostor syndrome or Dunning-Kruger effect.
You mean people not non-experts or no?
So the imposter syndrome is when you know stuff, but you think you don't know. Mm-hmm. And the Dunning-Kruger effect is the opposite, is you think you know stuff, but really you don't know.
Probably yes. I mean, the thing is that being totally anonymous, I'm thinking about why not? Yes, why not?
Yeah, I think they should be good to do that. We spent almost a year thinking about them and going around with them. So they're quite carefully selected to allow a bit of cross-checking to go on as well. If you've answered yes to this one but no to this one, it means, oh, there's a discrepancy there. You can't have that combination. So we should be able to find both of those syndromes with the seed, I hope.
Yeah. Yeah, they've been designed for that.
So that's been a big advantage of this long postponement. It's allowed us to iterate and fine-tune and get this exercise about as good as we can get it and troubleshoot it and find all possible errors and traps and pitfalls. So hopefully it's as bulletproof as it can be, but we'll always be here to be, if you like, the voice of the observatory, the people you phone up to seek help if there's confusion. Shall we make a coffee?
Yes, good idea.
Good idea. So let's
10 minutes?
say 10-minute coffee break and reconvene at 11 o'clock.
Good.
Great.
Okay, that's okay for me.
Brilliant. Well, thanks everyone. See you in a minute. Well, 10 minutes.
Nico, t'es là? Parfait. Alors, est-ce qu'on a des nouvelles de Jean-Christophe? Jean-Christophe, si tu es là, dis-le nous.
Jean-Christophe n'est pas là pour le moment. Aline tente de le joindre par téléphone.
Ok.
Donc, moi, je vais, alors, les collègues m'entendent, c'est pas grave. Je vais un peu meubler, s'il faut meubler, hein, en attendant. Sinon, on basculera sur la présentation d'Aline, mais son co-animateur n'est pas là non plus.
Ok.
Et voilà, donc bah, on va s'arranger. C'est pas grave.
If not, we still have Lucia is maybe here, so she can even start in case.
Ok. Mais ça aurait été plus logique.
Yes,
que ça soit...
Uriel, I'm here. Matthew, are you there?
Ah, on a 15 secondes, on est très large.
Oui. J'espère que Mathieu va aider, comme ça, c'est la...
Juste pour Auriel et...
Ok, c'est bon, il se connecte.
Oh, yes, it's okay.
Okay, perfect.
Jean-Christophe is coming.
Okay, perfect.
So
we will make a quick test with him when he's here, and then Nico, I'll let you start the session.
Okay, no problem. And could you keep the draw on just for 1 minute?
You want the drawing back?
Yeah.
Auriel?
Yes.
Before the presentation, can I just say one thing about the demographic sheet to everybody?
Yeah, Alessandro, the best will be if you can to write down everything so I can send it to the mail list. You can
okay.
add something now, but maybe
but it's just a clarification about the questions in the demographic sheet, that they will not be part of the seed questions, so they are something separate. Just that to reassure everyone.
But if not, maybe you take what you wrote on the slides. You write the email, so I forward it to the entire mail list.
Okay.
You know, so everyone is on the same page, even the one who were not here this morning.
Okay. Can do. Okay. Good. Thanks.
Nico, should we?
We go.
You want me to keep the drawing?
Till now, it's okay. Okay. I hope everybody is there. You are 42 now, and we are going to go ahead with this workshop. I'm Nicolas Villeneuve, and we've got 3 people who are going to speak this afternoon. It's because it's afternoon here in Union Island.
Morning here.
Yeah, of course. So please, for the speaker, could you respect the time? You've got about 25 minutes. And we're going to change a little bit the rule. If people want to ask some questions just after each participation, as Jean-Christophe, Aline, or Lucia, you will ask your question directly. Okay, and as Auriel said before, please turn on your microphone and your camera during the question, please. So Jean-Christophe, if you are okay, you can go on.
Yes, good morning, everyone. Sorry for the delay. I suppose I can share my screen.
You can do it directly from yours.
Yes, you can.
Okay, great.
Go ahead.
Okay, can you see the screen?
Yes.
Oh, but it's not the right one. Okay. Just a second. So this should be the right screen, right?
Yes.
Okay.
Can you just check that all the slides are going one after the other? Now it's dark.
Yeah, I don't know what happened.
Sometimes it's happened when you use 2 different screens. Have you got 2 different screens at home?
Yeah, but yeah, just a second. It should be it's because I tried to extend the window and therefore it's okay. So I would like to thank the organizers for allowing me to make this presentation. I will try to give you a quick overview of the current volcanic unrest that we have to deal with in France, and some aspects of the way we try to approach the crisis response management to volcanic risk in France. Of course, I will not talk about Piton de la Fournaise, and Aline, of course, will do that after me. I think I want to stress that we are at a particularly pivoting point for the volcanological community at large and the national community, because it's the first time we have so much volcanic unrest on the territory probably in the last century, and for actually several centuries, because we have of course, frequent eruptions at Piton de la Fournaise. We have a massive, long, ongoing eruption, submarine eruption at Mayotte, which I will discuss rapidly in a few minutes. And then we, of course, have volcanic unrest at Piton de la Fournaise, Soufrière of Guadeloupe, that's been going on for several decades. And as of last spring in 2019, actually 2 years ago, almost started an unrest at Mount Pelée, which forced us to recommend that we raise the alert level to yellow level. So we have quite a bit of unrest in the Lesser Antilles, and all our active volcanoes, except the volcanoes in central France, are presently in unrest or in eruption. And so this is a major challenge for our community. Of course, this talk is going to be a summary of a lot of work that is achieved by a large group of people that have acknowledged here in overall, and also some people, especially because of their particular involvement. And I apologize if I have omitted some colleagues. IPGP is responsible for the French scientific and national authorities of monitoring 4 volcanoes, Piton de la Fournaise in red. The green star above it is now the Mayotte volcanic area, and then the orange and green stars in the Antilles are the Soufrière of Guadeloupe, and in green the Montagne Pelée in Martinique. Now, I wanted to put this slide because as a result of the global assessment report that was submitted in 2015, in which for the first time volcanic risk was assessed globally, a new metric of quantifying the volcanic risk that different territories are exposed to was designed and was proposed, and that metric involved weighting the total population that is within 30 kilometers of an active volcano to the total population of the territory. And by doing so, there was quite a different map of global volcanic risk. And you can see that the region that was ranked the most at risk for volcanic activity is the Lesser Antilles, with Montserrat, St. Vincent, number 2, and France is number 3 and Dominica is also there, St. Kitts. And so obviously this is quite a timely thing to say, given the massive eruption ongoing at St. Vincent. But I also propose that if we would calculate this metric for Mayotte was not considered at the time. I think Mayotte probably is the region most at risk to volcanic activity, because we have nearly 300,000 people that live less than 30 kilometers, much less than 30 kilometers away from active volcanism, Holocene volcanism, and a little bit more distant from the current eruption, but the current eruption could evolve and generate activity closer to the island. So I think this is quite an important moment for volcanology in France because of these challenges. So we do this monitoring and the scientific crisis response with our different observatories. I won't go into great detail, but you can see here the second oldest volcano observatory in the world, the Martinique Observatory, which is now replaced by a brand new observatory that is not totally operation at this moment because of building problems. The Guadeloupe Observatory that was built in 1993, replacing an older observatory, and the Piton de la Fournaise Observatory, which was built in '79, and we have projects to build a new observatory or to rebuild on the main site. Just to show that these observatories are staffed with relatively few people, actually, and that is one of the main challenges, because basically we oscillate between 8 to 10 to a maximum of 16 staff in these different observatories. There are split in different types of staff with the engineer in turquoise blue. And you can see that there are differences among the different observatories. And this is excluding the Revosima, the Mayotte Observatory that I will discuss rapidly later on. And so we are actually short-staffed in many of these observatories. And despite of this, I think that our teams are doing an extraordinary job. And of course, the star of all these observatories is Piton de la Fournaise Observatory, as you know. The Mayotte Observatory is a very complex, actually, network. It's not an observatory that is residing in building walls on Mayotte. This is probably going to happen in the next few years, perhaps in the next decade. But given the urgency of the crisis, there was the need to set up a national network, and it's quite a complicated network because it involves, of course, a lot of institutions, and because the eruption is 50 kilometers away from an island by 3,000 meters of water, and it involves, of course, heavy recurrent oceanographic support for these missions, and that has made the whole network quite complicated, but quite successful in achieving what was achieved in the last 2 years. So this, you can just see the complexity, and this is one of the issues about crisis response in France, is that we have a very complex network with lots of layers. Some people actually would like to have more verticality in this organization, which would actually, we think, with Aline and other colleagues, cause a lot of problems. But we don't have a formal structure that gives us a clear mandate to do monitoring. Often monitoring is a taboo word. We have to use research, and then we have to try to come up with new expressions like operational research or operational observation, because monitoring is not supposed to be done by researchers, but there's no other structure that is doing this, and obviously we are constantly asked to support that task. So the monitoring networks are quite varied, but they're obviously the standard type with lots of on-site continuous real-time stations, about 245 permanent stations that are permanent continuous monitoring stations, and then about 220, probably more, campaign sites in the 3 observatories, and this is again excluding the Mayotte network. And the different disciplines are represented, and you can see here the different the proportion of these different disciplines, with, of course, a large part of the network in dark blue being seismology, in red the deformation, geochemistry in green, environmental sensors in yellow, and webcams in blue, and others is in burgundy color. Here's a snapshot of the Mayotte network, perhaps projected in 8 years from now, because we have just obtained a 15 million euro project from the French government that will allow us, hopefully, to build this cabled electro-optic cable network to 3 stations around the main area of seismicity, and we will have other optical stations linked to that network. The network will be secured here at the airport with electricity on the Petite Terre Island, which is just off the mainland of Mayotte. You can see the craters, the Holocene phreatomagmatic craters of Mayotte, all the assets of Mayotte. Most of the assets are here in this little island. And we will have additional OBSs and other campaign submarine stations around the area. And right now we have a terrestrial network with the seismic stations and in orange circles, and then GPS stations are the green triangles. There are also some magnetotelluric stations that have been installed by BRGM, and some of which are at sea actually. And so you can see that the main challenge is to have a monitoring network that will allow us to track and monitor the activity in this central part of the area. The active volcano is here. We'll come back to this later, but we have quite strong preoccupations that this area that has been very active in the past could reactivate. It's only located 15 kilometers away from the population here on Petite Terre and also on Grande Terre. And there are signs of unrest in this area, which the signatures of which are not clear at this moment, but there's lots of fluid emission here from different sites on top of recently or relatively young volcanic structures. I will go back to this later. So you can see that we have quite varied networks, and we're hoping to make a jump in the future with these electro-optic submarine cable observatories. We also have a network in the Caribbean in which we are responsible to transmit information within a few seconds to the Pacific Tsunami Warning Center. So we have a collaboration with all the islands in the Caribbean, including, of course, the SRC, for a satellite transmitted seismic and geodetic network. And this network allows us to document the ongoing regional seismicity in the lesser volcanic arc, the Antilles volcanic arc, which is quite active. So I will give you a snapshot of unrest at Mayotte, at Guadeloupe, at Montagne Pelée. Aline will talk about Piton-La Fournaise, and then I will address some challenges and problems and perspectives with crisis response in France. So Mayotte, you probably have heard about the occurrence of this massive submarine eruption here that formed a 800-meter high volcano. About 6 cubic kilometers of magma was emitted at the tip of this volcanic chain here that links this active center through this big chain where you see all these cones to the Mayotte volcanic island, in which you have Holocene phreatomagmatic vents right in this area. And the area of the most intense seismicity currently and has always been in this area within 15 kilometers of populated areas. So the crisis started in May of 2018. You can see here a chronology of a time series of the magnitude from 3 to 6 with time of the earthquakes that were recorded at the time, only with stations on land. So of course, the spatial distribution of these earthquakes was problematic and difficult on account of the geometry of the network, and there were some distal stations as well. And quite rapidly, we were able to install some OBS stations that were retrieved and redeployed about every 3 or 4 months. It might be too small for you to see. I apologize. But you can see here the seismicity, the VT, high frequency seismicity of the last month of March. So you can see Mayotte here. You have the main swarm that's located here within 15 kilometers. The active volcano is here, and there's a secondary distal swarm of VT earthquakes here. These earthquakes are notably located mostly below 25 kilometers depth. There's no seismicity being recorded above, and there are a few occasional earthquakes. And of course, these need to be relocated. This is a map before the relocation that is done using the OBS submarine data. And here you can see a map of the long period earthquakes that have been located in the area. And so you have long period earthquakes associated with the swarm distally from the active volcano. And you see that these long period earthquakes are also, they're part of the main swarm, and they're also located between 25 and 45 kilometers depth. Deformation has been followed by the GPS, continuous GPS network. There's also a station up here in Glorieuse, about 200 kilometers away. And you can see the GPS vectors pointing in an area between the main swarm and the active volcano. And you can see here the deformation trends, the motion trends for the relative eastern, northern, and vertical motion with a lowering of the deformation rate in the last few months and the stabilization of this rate, which is now almost with its near background levels. Although activity continues, seismic activity continues. This is a map of the compound lava flow field from the active center. You can see the main volcano here that was built about 800 meters high, and you can see the different lava flows that were emitted in the first year and a half of activity. And since August of 2019, activity is concentrated here about 5 kilometers northwest of the main volcano, with new lava flows being slowly emplaced. And there was an additional cubic kilometer that was in place in the last year and a half, since August of 2019 in this area. And when we were in October, we were able to dredge actually active lavas with incandescence that was visualized, that was seen by observers. And a recent survey in January also showed that there was new material coming out in this area, but relatively small volume, but it is still erupting at this moment, nearly 2 years, 3 years, nearly 3 years after it began. Here's a snapshot of the area to the northwest, and you can see the compound lava flow field with the different lava flows superimposed on each other. The yellow boxes are sites where we dredged, and the red polygon is the site of incandescent lava flow, active lava flow that was dredged in October of 2020. Now, the issue with Mayotte is the fact that we have, of course, gotten a great deal of resolution in the data on the submarine geology of Mayotte. There was already an indication probably about 15 years ago that there were quite a few cones in this area, but the numerous campaigns, up to almost 20 oceanographic campaigns in the area since May of 2019, have allowed us to map in quite detail the area. And you can see that there's a variety of volcanic edifices. In purple are probably paraclastic dominant seamounts. In orange are more lava dominant seamounts. There are large funnel-like lava flows emanating from perhaps an arcuate structure here that could be corresponding to an older caldera type structure. And they're also in pink, they're also phreatomagmatic Mars and tuff cones, submarine tuff cones, down to about 1,500 meters of depth. And of course, the phreatomagmatic vents here on island. The main volcano, active volcano, is here. And so you have this impressive chain with about 300 identified cones at least. There's a series of eruptive dikes and fractures, and these fractures are basically propagating towards Mayotte. Here on the right, you see a detail of this area, which is named the horseshoe-shaped area. The green stars are all the sites that have been identified during the submarine cruises in the last 2 years, where we have emission of fluids, dissolve gas droplets, actually probably a mixture of CO2, methane, H2S, hydrogen, and these can rise up to 1,000 meters in the water column. And they're all located in this area of a major submarine collapse. But this is a large paraclassic cone that we dredged in October in several places. You can see a tooth cone here, submarine Mar tooth cone, and you can see the overlapping, the great number of overlapping cones and lava flows and domes in this area. So this is really the area of great concern because it has been very active in the past. This is, if you make a map of the density map of the cones, you can see here that this area, the Fer à Cheval, is probably the most active area in the whole chain, with large volumes being produced in addition to the active site now. And of course, there's some data from seismic tomography that suggests that the main mush and transcrustal magmatic system is located below this area and is feeding with different branches the active site here and also volcanism on Mayotte. So we are really concerned that the current activity is actually also associated with the reactivation of this transcrustal magmatic system, which could trigger further propagation of magma to shallower levels towards the island. Now, this eruption is a very unusual eruption. It's lasted almost 3 years. It is the largest effusive eruption on Earth since the Laki eruption, with a relatively large eruptive volume, 6 cubic kilometers of effusive material, with eruption rates that have reached probably at some point 200 cubic meters per second, and have now, of course, decreased, but it's still ongoing after 3 years. So it's probably also the longest submarine eruptions known. We are working with the authorities, try to summarize all the information in this sort of table, and also in a decision tree with the different scenarios, and trying to address the elaboration of alert levels and thresholds, and this is all work to be done.
Jean-Christophe, you've got 5 minutes more.
Okay. Okay. So unrest in Guadeloupe. So there was a major unrest that began about 20 years ago, but it peaked in 2018 with what we thought was a near miss of a phreatic eruption, with a lot of activity from those fumaroles. Here you can see a map of the seismic activity linked to the 2018 activity that was described at length in the paper by Moretti et al. So I won't go in great details. I don't have much time left. Here is the data, the vector field from the GPS, the campaign GPS and the permanent GPSs, and we see that we have a field of radial inflation linked to a hydrothermal pressurization in the active areas, but we also have a slow basal sliding of the volcano with these larger vectors towards the south. François Bauducel and colleagues are modeling the GPS data, and you can see here a probability map of the location of the most likely source of the current inflation below the volcano, which is linked to the hydrothermal system at shallow levels. Roberto Moretti and colleagues have done a lot of work on the chemistry of the gases, and have indicated that when we had the major earthquake swarm and the 4.1 magnitude VT earthquake below the dome, we had this corresponded to the most magmatic signature of the gases emitted at the volcano. Seismic activity is very intense since 2018. You can see the different swarms. Here in the red bands are different seismic swarms, and this data goes until the current time. And so you can see that we have very frequent earthquake swarms in Guadeloupe. So we basically think that we have had a pressurization and an overheating of the hydrothermal system due to periodic injection of magmatic deep fluids from the mush system. from a depth of about 6 kilometers, pressurizing the system here and causing the main surface activity. I will go quickly to the unrest on Mont Pelé, and then I will remain for the questions. If you have questions on the crisis management, you'll have the PowerPoint in the packet of the workshop. So Mont Pelé, we've had a significant seismic unrest that began in April 2019. You can see here the cumulative VT seismicity in numbers since April of 2019. You can see here the numbers per month, and this stops at December. We just published our December bulletin, but we are continuing with the seismic activity. You can see here the seismic activity since January with lots of earthquake swarms, low magnitude earthquakes, generally below a magnitude 1, and shallow earthquakes located maximum 2 or 3 kilometers from below the summit, but there are some deeper earthquakes down to 6 kilometers. We've also recorded long period earthquakes and bands of tremor in November. You can see here these tremor bands that were detected in November. We've had several episodes since then, and you can see here a map of the location of epicenters since December, from December to January, and you can see the location of these earthquakes that reach about 4 kilometers depth right below the volcano. We've also noticed by eye and then by satellite imagery that there was an area of burnt or degraded or vegetation, and this area is here on the upper flanks of the volcano, and this suggested to us that perhaps there was a sign of increased CO2 diffuse degassing from the ground. And also we were preoccupied by the presence of these lineaments that we could notice by helicopter overflight. We managed to be dropped by helicopter in the area, and so we noticed, of course, these areas of extensive burned vegetation with the sublimates covering the vegetation in different spots, and some relatively fresh, frank, open fractures in the area. So we made with the equipment that we had. It was only a gas security detector. We don't have yet the equipment. It's being shipped right now from La Réunion, actually, and from the observatory. Andrea Di Muro is making a gift of that equipment to the observatory, and so we were able to detect that we had abnormal levels of CO2 in the ambient air. But of course, this needs to be correctly mapped with state-of-the-art equipment, but we could reach up to 8,000 ppm of CO2 in open air in the areas where you have the major vegetation kill. So this is a chronology of the observation for reactivation of Mont Pelé. Here you have the chronology of the VT seismicity. We have also recorded deep VT earthquakes with the depth here is indicated between 11 and 20 kilometers depth. A few intermediate earthquakes, and you can see here the strong increase in November and December of the activity with tremor in purple stars, in pink, the long period events, and then a few more deep earthquakes afterwards between January and March. Here you can see the gradual extension of this vegetation kill with the observation that we have probably CO2 being emitted from the ground. And we of course, given this pattern of unrest, and before we could even actually identify the vegetation kill, we recommended on the 4th of December that we go from green to yellow vigilance. So I think I better stop here and perhaps take some questions on the overall aspects of crisis response in the other areas than Piton de la Fournaise. Thank you very much.
Jean-Christophe, thanks very much for this very, very interesting presentation. Very interesting for French overseas population, but also for scientific community, I think. If there is one or two questions, it could be good for the time because it's a very important topic now. Oriel, do you see some question?
Yeah, Ben, go ahead.
Okay.
Hi, Jean-Christophe. Very interesting talk. Thanks. I was wondering on Guadalupe unrest, how do you differentiate hydrothermal from magmatic inflation?
That's a good question. One of the, I showed the slide, there is the modeling that is done by François Beauducel, and he's able to actually do a probabilistic modeling of the most likely location of the inflation source, given the magnitude of the displacement and the geometry. And so he has he's able to locate this source in the shallow part of the edifice. Of course, we can see that the deformation only affects maximum 1 kilometer depth, so it's obviously a very shallow sourced deformation, and it's also, of course, correlated with the current high activity, degassing activity in the fumaroles. We also have extension of the fumaroles that we measure with the different techniques, and we also have very shallow seismicity linked to those areas.
Okay.
Thank you.
Is there another question? Okay, if they're not, we are going on. We are going on the following speakers. There are two. They are going to speak about volcano crisis management at Piton de la Fournaise. They are used to work several times together. Aline Pelletier is from OVPF, and Stéphane Rennes is from the local civil protection called here État-major de zone et protection. Oh, he will say it better than I. Thanks for them, and sorry, Stéphane.
Nicolas, if I can just say, there will be time for questions later today. So if you have questions, just don't hesitate to keep them for later.
Okay, and I've got time also to say État-major de zone et protection civile de l'océan Indien. Sorry for that.
Thank you, Nicolas. So before to start, and as Andy told you, we are in eruption at Piton la Fournaise now since 3 days. So we are very busy and tired at the observatory. So in advance, sorry if I won't available during all the time of the workshop. Second point, and because I did my talk 2 weeks ago, I didn't have time to update this presentation with this new volcano crisis, but do not worry. The example we took into consideration in this talk is very representative of what we do for management of each eruption on this volcano. So the aim of this talk is to show you how the observatory and the civil protection interact for the response to the Piton la Fournaise unrest and eruptions. And before to present that, I quickly show you the context of this volcano. So Piton la Fournaise is a currently active volcano of La Réunion Island. It builds on the eastern side of an underdog volcano, Piton des Neiges, which is currently dormant. And as you can see on this map, the fissure in blue, most of the activity occurs in the center part of the volcano. So inside this caldera here in yellow, which is completely fully uninhabited, but visited each year by 100,000 of hikers. And sometimes fissure can open on the rift zone to the north, to the south, or to the west. Now, regarding the last decades, the last 3 decades, century, sorry, 97% of the lava flow were enclosed in this caldera, and most of this activity is effusive, with lava fountaining, lava flow, but sometimes with some consequences for the population, as you can see on this slide. You can see that sometimes it can have effect on the vegetation. The vegetation is in green here. as observed in 2019, where we have fires in the vegetations. Sometimes we can see the road, the national road here east of the Encre caldera, sometimes cut by lava flow, which occurs 8 times during the last centuries. And for 2 cases, in 1977 and in 1886, 2 lava flow which reached a village with some buildings that have been damaged by lava flow. And to finish the slide concerning the context and to have a few numbers in mind, and not for the exercise tomorrow, since the creation of the observatory in 1979, we anticipate at the observatory and monitor 80 eruptions, 81 now with the one ongoing, 2 pit crater collapses, 1 caldera collapse, and for the total of 1,861 days of eruptions and 758 millions of cubic meter emitted of lava in surface. And 3 last numbers is the mean duration of eruptions, 19 days since the creation of the observatory. The mean volume of emitted lava is 8 million of cubic meters, and the mean effusive rate is 7.7 cubic meters per second. Just for information, for the moment at Piton-la-Fournaise with the ongoing eruptions, we have effusive rate comprised between 10 to 20 cubic meters per second. So to anticipate and follow this eruptive activity, an observatory has been created in 1979. And currently we have about 100 sensors on 69 sites on the volcano, mostly on the Piton-la-Fournaise volcano, but also on the Piton-des-Neiges volcano. Mostly we have 40 seismometer, but also GNSS receiver, tip meter, extensometer, gas stations, NOVAC stations, and webcam and infrared camera. All these stations send their data in real time to the observatory located here, 15 kilometers away from the summits. That allows the scientific teams to work in real time on this data, both from the observatory or from anywhere from in the world, from the web via the internet platform. So all this network allows the observatory to alert the civil protection for any change of eruptive activity. And I let Stefan present you the emergency plan.
Thank you, Aline. Do you hear me? It's okay?
Yes, it's okay.
Yeah, okay. So in order to organize the civil protection response in link with the eruption, the local authority decided to create an emergency plan, as you can see. This plan is specific for the volcano eruption and describes how to react in civil protection terms with different local services like firemen, police, etc. According to the different levels of the eruption. So I will detail you the 4 main levels. The first one is the yellow level, which corresponds to a possible eruption or possible landslide. Is called vigilance or alertness, if you want in English. And then we've got the orange level. This level is when the eruption is upcoming. The third level, called Alert 2. This is when the eruption is in progress. So like in this moment at the Piton de la Fournaise. And the last one, the last level, is the level called backup or sauvegarde in French. And this one is after when the eruption is over.
Thanks, Stefan. So we show you now the example of a crisis management at Piton-la-Fournaise with the example of the April 2020 eruptions, so the last years. So at Piton-la-Fournaise, we have 2 kinds of precursors that anticipate eruptions. The first one occurs on the long term. That means that we have a few days to a few weeks up to a few months before an eruptions, an increase of the seismicity, an inflation of the volcano, and an increase of the CO2 salt degassing. So thanks to these 3 parameters, we can anticipate early enough the eruptions. So for these eruptions in April, so I show you here the daily seismicity between November 2019 and April 2020. So we have 3 eruptions in red here, the October 2019, the February 2020 eruption, and the April 2020 eruption here. And for the April 2020 eruption, we can see the increase of the seismicity a few days before the eruptions. This seismicity was located just below the summit craters at about 2 km depth, just above the main shallowest magma reservoir. At the same time, we observed an increase of the CO2 soil flux in the far field of the volcano. That means that we have a deep magma refilling from mountain levels from 20 km depth to the shallower level. And at the same time, a renew of the inflation of the volcano. We have here the basalt chain of the summit, and we can see the inflation of the volcanoes that start a few days before the start of the eruptions. The source of the inflation is located at 2 km depth, center below the summit crater. You can see here the displacements linked to the inflation stage. So all these parameters, so soil CO2 through degazing, seismicity located at 2 km depth, and the source of deflation located here at 1.5 and 2 km depth, means that we have a refilling of the whole plumbing system from mountain level to the shallowest magma reservoir located to 2 km depth. So when you record the first sign of the renew of the seismicity of the inflations, the observatory directly call the civil protection and write a bulletin, a report for the civil protection so that it can trigger the earthquake plan.
Yeah, so we are actually in the yellow level, and in this level we are monitoring the situation thanks to the observatory, thanks to the automatic daily email that they sent us. One specific point you have to know about the different civil protection measures in the enclos. It is in this yellow phase, only 3 hiking trails are allowed in the enclos for people. But this is the only measures that we have in yellow level.
The second kind of precursor are the short-term precursors, which occurs between 10 minutes up to a few hours before an eruptions. And we show that for these eruptions with the seismic signal on this recording. So I show you here the seismic signals occurred just before these eruptions. So we can see that 8 o'clock in the morning, 8 o'clock past 20 minutes, we have what we call at La Réunion a seismic crisis. So at that time, when the seismic crisis start with strong deformation and degassing, we know that the magma is leaving the shallowest magma reservoir and that an eruption is very imminent. So we call, so at that time we have an alarm, an automatic alarm, which calls the person in duty at the observatory. So when we have more than 3 earthquakes in 1 hour, so at that time, we call again the civil protection to tell them that now the eruption is imminent so that it can trigger the next level.
Yeah, that in this moment, we increase the level of civil protection response. So we are in alert 1. Next slide, please, Aline. Yeah, and at this moment, we have different steps in order to respond. So the first one is to warn the departmental authority, le préfet. And then we send a text message to the different service to warn them about alert 1. So it's different, like firemen, police, but forest office and others. Then we call the police air forces to fly over the Enclos Fouquet. This reaction is to evacuate the hikers inside the enclos before the eruption. So we need time, and we need to do that immediately. Then we have to proceed to draft a closing bylaw to close the gates officially. And this is the forest office that they will put this bylaw at the gates. Then we have to inform the national level by phone or by a software called Synergy. And then we inform the population through the official on social medias.
On the observatory side, during all these periods that can last, so I told you a few minutes to a few hours and sometimes a few days, we organize a crisis meeting. So either in the crisis room during working days, as in these pictures, or on a dedicated dialogue room as during holidays or during the COVID period when we are in lockdown. So during that time, the scientific staff interact to work on the data and to precisely detect where is the magma in depth and to communicate this information to the civil protection. So for these eruptions, both the deformation and the seismic data show a propagation to the eastern flank of the volcano. So we can see this with the automatic deformations modeling, the migration of the source towards the east, and the same with the seismicity, with the migration of the seismicity from the summit to the eastern flank. At midday, past 15 minutes, a new signal was recorded on the seismic signal of the observatory. This is here, this signal, which increased progressively, which calls a volcanic tremor. So when we observe this signal of the seismic signals, we know that the eruption is start very soon because it's linked to the arrival of the magma in surface. So at that time, again, we call the civil protection that the eruption is ongoing. For this eruption, thanks to the map, the tremor map, we can locate the fissure active to the eastern flank, like as observed on these figures.
Yes, in this red level, it's not the same emergency because normally there's no hikers in the enclosure. So now the main goal is to send an helicopter to the observatory in order to find the exact place of the eruption. But we have some same steps that the alert one. But the most important for us now is to assess the potential lava flow away, thanks to the simulation that we will show you just after. But this is the main important information for us because thanks to this simulation, the civil protection response will be totally different. So we here in La Réunion, we use a police helicopter to send it to the observatory in order to take photos and to geolocate the eruption. And then we've got this simulation. For us, it's a new tool, very useful. And thanks to Clermont-Ferrand University and thanks to the observatory, we have a very, very good tool in order to warn the population, to warn the different aspects of the eruption and the different impacts. So for instance, we've got different impacts in this area. The first one is the forest impact. As you can see on the first picture, we can send firefighters to this area, and we can use firefighting planes or helicopters in order to extinguish the forest fire. And we have different measures like closing the hiking trails, thanks to the forest office, and close the road because there's a road near the eruption. And the main impact will be if a village could be impacted. And in this case, there's different measures to take, and the most important one is to evacuate the residents of the different villages, and the closest villages of the Piton de la Fournaise are not very big. It's around 2,000 people for Piton Sainte-Rose. And the most preoccupied evacuation that we have is about Saint-Philippe and Saint-Joseph, because Saint-Philippe is around 5,000 residents, and Saint-Joseph it's around 37,000 people.
So during that time, so when the eruption is ongoing, observatory are some protocols. So the duty protocols are reinforced with a routine manual check for the continuity of data acquisition and the volcanic eruptive behavior. The check is made every 4 hours, so during days and night. And in case of any change in activity, the director of the observatory is informed and information is relayed to civil protections. During eruption also, we have daily exchange with the civil protections, and the observatory write daily reports, and for any change of activity, also sometimes many reports in one day. And of course, these daily reports are sent to the observatory, to the civil protections, and put in the social media of the observatory and on the network, so that the general public can access to this data. During the eruption, the observatory organized also a field mission for field observation to sample lava flow, to do complementary acquisition for gas emission, deformation, thermal imagery. So, for instance, the lava sample are directly sent in mainland, both in Paris and in Clermont-Ferrand for analysis. And in the same time, the observatory can also rely on its dense network to continue to remotely follow the eruptive activity. So for this, we have, of course, the webcam, the daily seismicity, the seismic amplitude, the deformations, the SO2 flux that can give an idea of the effusion rate. And in addition to these field networks, we have collaboration in the framework of national and international collaboration to have access to remote sensing data as the one, as the one that we can have with the Outvolk platform and the New York platform for the effusion rate, and also with the INSAR, thanks to the University of Clermont-Ferrand, for instance. So that can have access of more data, but this is very adequations and in continuity and complementary of the observatory data, so that we can have a full range of data, both from field and from the satellite. So with this all data set, we can alert civil protection in exchange of eruptive activity. So this change of eruptive activity occurs, for instance, in April 5, 2020, during these eruptions, when we have an increase in the effusion rate, an increase in seismicity. So at that time, we were, during the lockdown in France, we call again civil protection to have access to gendarmerie observation from the road, to have more information on what happened in the field.
Yeah, no more, because this is a reality. If we need some information on the ground, in the field, we can ask, thanks to the civil protection chain, the different services like police, gendarmerie, or the firemen, because they are in this area, they are present with different stations, so we can use them.
And finally, so at the end of the eruption, so we can have news of the end of the eruption thanks to the seismic data. So we have a spectrogram on this slide, so we can see the student end of the eruption for this case. 50% of the eruptions end abruptly, as observed on April 6, 2020. So at that time, we know that we have no more tremor, so that we have no effusion rate in surface. So at that time, again, we alert the civil protections as like no more activity, but sometimes we can have a residual seismicity, residual degassing, residual inflation. So we give this information for the civil protection that can trigger the safeguard element.
Yeah, this is a safeguard level or backup. In this level, can you, the other, oh yeah, thank you. In this level, there's, we have to make an expert teams in order to assess the different consequences of the eruption. The goal of this assessment is to open after the different analysis the enclos Fouquet to the population.
So to conclude this presentation, so now we have 40 years of feedback at Piton-la-Fournaise. So we have the successful monitoring of 81 eruptions in 40 years, thanks to existence of a well-established response protocol, notably via the emergency plan ORSEC. Each service knows well its mission at the observatory and the civil protections, and we have the proximity of each actor of the emergency plan in the field in La Réunion.
Yes, in order to conclude, we would like to conclude with this simulation, because this is the job of synthesis of our needs in civil protection, and this is very important for us to work together with the observatory and with the University of Clermont-Ferrand in order to have new tools, in order to have a better reaction and a better civil protection response when we've got an eruption in La Réunion.
Thank you, everybody. And if you want more news on the Piton-la-Fournaise activity and the current activity, you can go on the OVPS website and social network, as well on the Prefecture of La Réunion. Thank you.
Thank you.
Thanks very much, Aline and Stéphane, for this talk, and you respect perfectly the time allocated to you. I don't know when Stefano stopped the slide, because he said us that there was some problem. There was some problem with slide. Stefano, could you tell us if it stopped recently?
Well, the last slide I can see was with the eruption, but I don't know.
I can share my presentation if you want.
Anyway, if you're going to share all the presentations somewhere, yeah, we can check it later. Thank you.
Okay, thanks, Stefano. Thank you very much again for the respect of the time, and like that, we've got a few minutes for questions if some people need to ask. Benjamin, you can ask it directly.
Okay. Yes. Can you hear me?
Yeah.
Okay. I was just asking Stéphane Dren, how quick is the civil protection response to the scientist advisories?
Immediately, because we are in a phone call. So they have our duty officer phone number, so they can ask us what they want at each moment. So if they need an helicopter, we can see if the helicopter of the police is available or something like that. So there is no filter between the observatory and the civil protection response.
And for example, how long does it take usually to evacuate the hikers or something like that, or to close the road?
It's a difficult question because it's not the same each time, of course. But as soon as we've got the alert 1, we send an helicopter from the police, and then it's around 30 minutes flight. So it's very quick. It depends on the availability of the helicopter. This is one of the parameters that I can't. I never know if it's available or not.
Thanks so
and
much.
for the road, maybe?
For the road, it's different because we have some time. In fact, it's very not often that the road is impacted immediately. For the moment, during my 2 years here, but it's the police is near from the enclosure, so we can do that first with police patrols at the beginning, and then the road services can reach the area and can put everything they need to stop the circulation.
Thank you very much.
Thanks so much. We've got two next questions with first Domenico, and then I think it's Lucia.
Yes, thank you very much for the very interesting presentation. I have two questions. The first one is in the alert levels you have shown there is, as I understood, a direct link with scientific data and actions from the civil protection. My curiosity is in alert level, the orange, in which you say eruption imminent. When you say eruption imminent, is this assessed by a probability, and which is the time frame of the imminent? Days, hours?
I can answer if you want, Stéphane. So for alert one is the moment where we have the seismic crisis. So when we know that the dike is propagating to the surface. So usually at Piton de la Fournaise, this takes between a few minutes. Sometimes it's only 10 minutes, and sometimes it can last up to 2 days.
Okay. So it is based on the knowledge you have of the volcano, correct?
Yes, exactly.
Okay. And the second question is more a curiosity for Stéphane. When you say in the slides, you call the National Civil Protection and Synergy software. What is Synergy software? It's just a curiosity I have.
Yeah, this is a civil protection software that we can put the different information about civil protection event in France or overseas, and we can inform our national authority thanks to this software.
Okay, thank you so much.
Okay, Lucia, please.
Yes, this is a question for Jean-Christophe, starting from Aline and Stéphane, because Aline and Stéphane, they show almost a perfect protocol of a crisis response between the observatory, the local authority, the research institute, and they had years of training with all these eruptions. So Jean-Christophe, would you say that you have the same protocol in the Antilles, or the fact that the Antilles don't have so much training there is a little bit more difficult?
Yes, I wasn't able to discuss this, but you'll see this in the presentation. We have the same theoretical protocol because we also have an ORSEC plan already for many years. There was actually one that was issued just a few months before the 1976 eruption. And then there's a new one in 1999. And then we just published one, well, not we, but we just revised one, and we contributed to that in 2018. And the Martinique plan dates to 2002, and we are now presently working very hard to do it. It's supposed to be signed by the Préfet at the end of April. So there's a standard protocol. We have the same overall parts, except that we don't have the sauvegarde part. And it's actually an interesting point, because the authorities looking at the Piton de la Fournaise ORSEC plan, which is taken to be the best one, they wanted to put a backup, the sauvegarde phase for Montpellier, and this doesn't make sense actually, because the sauvegarde phase for Piton-la-Fournaise is very specific to the issues that were just discussed by Stéphane and Aline. So we have argued against that, although of course it's important to be aware that descending levels is a challenge, and I think we can exemplify that with a different way rather than creating a specific section for that, because it's hard to know exactly what type of activity we're going to have. So going back to your question, of course, it's never been practiced in real, but we did one exercise in 2019 at the initiative of the Préfet of Guadeloupe, but it was kind of a mix of a table. It was a table exercise, but it involved real actors in the sites, but not the population. And of course, in Martinique, there has been no practice and basically no unrest in the last 90 years. So yes, it is going to be a problem, and we have daily issues, actually complicated issues with the authorities. And unfortunately for St. Vincent, it's a really tragic eruption, but I hope that this is going to be a reality check for the authorities, because we've been proposing them a variety of things, argumenting, documenting why you need to consider not just the evacuation. Evacuation is not the only solution. You will need to live with nuisances and dysfunctional systems and problems in the zones where evacuees might come. And well, the situation in St. Vincent, of course, shows it. We've stressed that ash is the most problematic hazard, because the other hazards, you can have some kind of zonation and the evacuation will partly deal for that. But ash is going to be even in the area where people are far away from the volcano, as we see in Barbados and we see in many other times. But they are reluctant to take all of this knowledge until they really see what it is. So I think now that St. Vincent is hopefully going to open some doors to try to set up this plan, but it has to be practiced once it's elaborated.
Thanks so much, Jean-Christophe, for this very complete answer. I think it's okay for questions, and now we are going on. And as it's not evident on the program, but we are going to have a contribution of of a pair of researchers, Mathieu Gouillet and Lucia Gorioli from the LMV. They are going to speak about contribution of OPGC to volcano crisis response. And they are from LMV in Clermont-Ferrand.
Okay. Thank you, Nicolas. Everybody can hear me? Yeah? Okay. And Lucia, you change the slides, or it's Oriel? That's you, Lucia.
Lucia.
Okay, perfect. Let's go. So first of all, thank you very much to Andy and Oriel for handling all that despite the lockdown situations, and for inviting us to the presentation of VGC contribution to the effusive crisis at Piton-de-la-Fournaise, which is going to be presented by, we share the presentation, as said Nicolas, with Lucia and I. So you can change. Lucia, you can change the slide. Next, yeah, thank you, perfect. So basically, OPGC activities represent 12 observation tasks and 2 operational model-driven responses, which can be actually divided in 4 thematic groups: remote sensing, analysis, drone, and modeling. And in this framework, OPGC activities are integrated to the National Service of Observation in Volcanology, namely the SNOV, as already mentioned Jean-Christophe just before. And in the particular case of operational response to effusive crisis, we are going to present here the INSAR system, deformation modeling, IR remote sensing system, the rock analysis, which is going to be presented by Lucia in particular. And this afternoon, we are going to have a talk from OIL on lava flow modeling initiated by Andy and OIL. Okay, I'm not going through the complex organigram of HSA, but I said, well, take-home message already. So you can change the slide. Thanks. Okay, for the system named OE squared, which is satellite-based radar interferometry system labeled by CNRS in 2010, which is the service in charge of satellite-based deformations monitoring at Piton de la Fournaise, existing since 2003. It has acquired about 2,000 SAR images, which make an average one image every 2.2 days and allows us to monitor about 43 eruptions and 3 intrusions since 2003. And today, Jean-Luc has implemented Sentinel-1 routinely. And from 2003, this is basically more than 10,000 interferograms calculated by the OE2 system. Regarding the deliverables, you have basically ground deformations in the form of interferograms. You also have displacement patterns, quantitative displacement patterns in the form of east-west and up-down maps. And of course, lava flow areas from coherence maps, and sometimes the information on lava thickness as well. I'm going to present some examples about all that. And the data are accessible through the Casoar interface, which is hosted by OPGC and accessible from the web address. So this is an open access, but you need to subscribe, just subscribe to the service and you will access all the data through the course. So you can change the slide. Next. Okay. So two nice examples, two eruption examples of deformation and lava flow. On the left, you have interferograms calculated from spotlight data at Piton de la Fournaise during June 2019. I don't have the bottom of the slide, but I guess this is the right date. And you can see the deformation from the series of fringe cycles on the left figures. And on the right, interestingly, you can also see a very accurate map of lava flow contour and hence area from INSAR coherence. And it's a very precious kind of information on the footprint of the lava flow on the ground. Let me change this slide. So a very recent example, actually, it did the last intrusion from last September 2020. You can see the pattern on the left image, which is completely different with a large number of fringe cycles, which traduce actually a very large displacement. And this is actually what we can see on the right image, where you have two maps. And this is the maps of the east-west and up-down displacement, which reach a spectacular level. You have east-west up to 90 centimeters, and up-down displacement is up to 70 centimeters. So to my remembering, there is no eruption related to this intrusion, just purely intrusion activity. So now what about DevVolc, which is the volcano deformation modeling associated to this INSAR team? From the deformation map produced by the INSAR team, the best fit deformation model evidenced the presence of a fracture located at 1,000 meters below the surface, which corresponds to a sheared intrusion rather than a fault. So systematically from this modeling system developed, we are trying to go back to the source of the deformation observed on the ground. So you can change. Next, please. So another very nice examples, especially on the left panel of each figure, you can see here the lava thickness that can be basically obtained from the difference of radar DEM from images before and after the eruption, which gives you a very accurate estimation of the lava thickness at each location of the lava area. And you can see, for instance, on the top left panel, at the vent location, you can have a lava thickness reaching 30 meters high. So it's very precious for us also to have this kind of data. Okay, next, please. So I move on the next system, which is the system Hotbolt, which is a space-based infrared system labeled by CNRS in 2012, and which is the service in charge of satellite-based lava flow monitoring at Piton de la Fournaise using Meteosat Severity data, and operates in real-time fashion with frame rate images at 1 image every 15 minutes, and a spatial resolution up to 3 by 3 kilometers at Nadir, but of course it's much larger than that at Piton de la Fournaise location. The deliverables are twofold: level 1 data, as for instance total spectral radiance plus number of spots, and level 2 products such as lava flow discharge rates, ash concentration and altitude, and sulfur dioxide ground. We have basically 50 different volcanic targets, but most important for us are France, Piton de la Fournaise, Soufrière de Guadeloupe, and Montagne Pelée, of course, Iceland, Italy, Cape Verde, and some interesting targets in Africa as well. So since 2018, Hotbolt system comes under official duties of Météo France for the volcanic ash fields. So this system allows us to monitor since 2015 about 25 eruptions at Piton de la Fournaise, and the data are accessible in open access through the Hotbolt interface. There is a PC version, the most complete and updated, and a light mobile version as well. Let me change the slide. Thank you. Here is a very nice screenshot example of the interface during the August 2015 eruption, which was a very large effusive eruption. So in this screenshot, you can see the red pixels, which are flagged, which identify yes or no, there is a lava flow underground. So you can have a series of pixels here saying that you do have a lava flow underground. And the light green cloud represents actually the sulfur dioxide plumes going out from the vents. At the bottom of the screenshot, you can see the time series, which represent the instantaneous lava volume flow rate, the EFR, given in cubic meter per second and provided in a real-time fashion during the course of the eruption. So you can access this operationally. You can browse interactively the large set of data here. And of course, this is open access. And by registering, you can download the CSV data at the bottom right of the time series and GeoTIFF product of images. So you can change. Next, please. Okay, perfect. Thank you. So here, it is a nice example on the same eruption. You can see here that the surface lava emplacement, bottom sketch, is almost synchronous with the lateral near-dike deformations. And in this eruption, the eruption began around 2:50 p.m. and this eruption could be confirmed from the Volc system at 3 p.m. in just 10 minutes later. Of course, to be honest, it's not always so good. I mean, because it strongly depends on the weather conditions and sometimes satellites are blind. So the quantifications of lava volume and discharge rate are obtained from estimating the instantaneous volumes calculated from space thermal mapping and by modeling the cooling rate between two successive events. Next. Okay, and to finish my part, we recently updated the platform and add the eruption catalog. This is the green button at the left, yes, and where you can access all eruption archive from Piton de la Fournaise, of course, but not only, with a large variety of parameters, lava volume flow rate, radiant energy, hotspot number, etc. So you can access. And you also have metadata information about the fact that you have or not ash and SO2 for a given eruption. And finally, you can also access to the official report generated after each eruption. Thank you very much. And I leave the floor now to Lucia.
Thank you, Matthew. So we will pass now from real-time continuous flow of data from the sky to rock analysis. And or as in now fashion to say petrological monitor, but we are not allowed, that Jean-Christophe pointed out. Anyway, this petrological monitoring that I saw fashion in the French community, in the volcanological community of the world, started, I think, at Piton de la Fournaise since 1981, Patrick, if you want to correct me, something like that. So we are just carrying on what has been started years ago with a big effort from Clermont-Ferrand, but in strong integration with the observatory of Piton de la Fournaise and of course the Institute in Paris, IPGP. And this approach, I'm presenting this approach for Piton de la Fournaise, but a similar approach, a little bit bigger because there is other institute involved, as Jean-Christophe showed, is applied for Mayotte. So we are doing the rock analysis for the active lava at Mayotte as well. So here is the list of the people involved. You can see is a long list of both from OPGC and IPGP. I will be focused on OPGC today, but as I say, the two coordinators of this effort, it's me from Clermont-Ferrand and André Di Muro from the Observatory of Piton de la Fournaise. Next. So the first step of this effort is the sampling that is performed by coordinated by Andrea, but as well as the OVPF teams, and sometimes the OPGC teams, as recently Auriel, Chevrel, and Lydie Gaillet were involved in collection of these samples. So this is the first challenge for us. We are not lucky as the people in Catania that had the scorium just falling on the town. We have to reach the active site, and is not easy. Here you have in this first picture the photo of the fracture that opened the 9th of April 2021, and in red the front of the lava in the 10th of April in 2021, and then the activity just pictured yesterday from Andrea and other people close to the active fountain. And then I think Zaline down collecting the active lava flow. So it's quite a big challenge, both to do the scene and the post-eruptive sampling. And it can be a challenge also to go back to the base, because sometimes they are dropped by the helicopter, and then the helicopter cannot go and pick them up. So I want to say a big thanks to the people from the observatory, because they do a lot. And to bother them, we set up with them, of course, a protocol that has been published in 2017, the way in which we should sample the lava to be representative. So lava should be quenched, and we should always sample close to the active vent for having the flow source condition quantification, but also along the channel to quantify cooling crystallization rate. And we should sample the front throat at the beginning, during, and the end of the eruption, and with appropriate tools to avoid contamination, especially for Ivan that works on the truss and isotopes, and use high temperature ceramic tools or tools made with basalt from Piton. So this is the protocol, this is the theory. Actually, we sample what we can and what is safe to sample. But anyway, it's always great, the products that the observatory team is able to provide. Next. And here, what we did today, what we started this time is to make a chronometer of the time that we needed to do this famous petrological monitoring. So, as I said, the first step is sample. And if the weather allow, the researchers to go to the field during the eruption, and then to work on the sample to store them, because samples need to be dry and divided between samples that need to stay at the observatory and the others that will be sent both here in Clermont to Paris, but also make the samples available for the general international community. Then to enter the sample metadata information, that Andrea is in charge of that, so who collect the samples, at what time, the GPS position and everything. And finally, we receive the sample, that can take 1 or 2 days to come. This morning, Aline and Luciano just sent the AKL to allow us to have the samples from yesterday, today or tomorrow. And we made a list. I did that with the colleagues here, and Pascal and Andrea. We made a list of the measurements that we perform and the time that it requires. So as you can see, there are fast measurements that we can do soon, and other that are provided with sometimes later. I'm not going through the list, but I'm presenting some of the results that then will help to make some kind of cyclicity in the data, and to provide some kind of quantitative information about the magma characterization, storage, timing to come, and or its unrest time. So here is an example of the density porosity measurement that we started since the first eruption of this new cycle in 2014, and here the vesicularity gives us a first order of indication about the texture of homogeneity or heterogeneity of the magma, and it tells us about the gas content or its loss. So here the average vesicularity we do expect is around 50%, as you can see from the middle photograph of a quenched lava. But you can also see that you can have variation and have a more vesiculated lava that is usually happen at the beginning of the phases, but also lava that is degassed on the left, like the one that we have in 2014. And sorry, we had the problem with the children. Lava degassed in 2014, all lava rich in olivine. So for us, it's incredibly important to work out which kind of lava we are looking at. And the leaf, let me, and I don't know how to, so okay, here instead is the characterization of the glass, both in lava fragment in and pyroclast products that can be scoria or what we call the golden pumice, that are the most vesiculated products. So of course, the highest temperature in the glass are recorded by the golden pumice. And you can see we are at the beginning of this time series of data. As I said, we start in 2014, but you can already see some kind of trend. For example, recently we are achieved the highest temperature of the magma that you can see in the first graph, and you can see in the second graph below. You can compare the variation in temperature with the MgO content in the bulk rock, and you see there is not a strong correlation. And for example, in the eruption of 2015, you have an increase of MgO due the arrival of olivine, but this increase is not marked by an increase in temperature of the pre-eruptive magma. Instead, now it seems to see both in the last products of this eruption in 2020. And so before, if you paid attention, I forgot to mention it, there was a zoned olivine. So the presence of these crystals that are zoned allow us also to perform some great quantification about time constraints, and also the composition of olivine can help us to place this magma in deep. So if you remember what Aline showed, she showed the seismicity with the high. What the petrologist, we like to instead picture the magma reservoir. And here you have different reservoir from deep, 8 kilometers up to the surface, and depends on the content of first in the olivine, we can state if we come from deep or not. And also making the diffusion profile in this crystal, we can quantify the resident times between magma mixing and eruption. So this is work that has been coordinated especially by Andrea Di Muro with colleagues from Germany or another part of the world. But this is a great work that we want to now try to make more routine driven quantification. But the best time series data has been achieved by Ivan and all of us, but this work has been led by Ivan Vlastelik because he managed to show that looking at the isotopes elements, especially strontium here, he managed to look at the variation in the magma driven not by the shallow chambers that I showed, but mostly by the composition of the mantellic source. And so high isotope value are related with the high fertile magma. Instead, the depletion of this ratio is correlated with the depletion of the melting material in the maltol source. So as you can see, Ivan managed to find a kind of cyclicity in these products that started in 1950. And now it seems in 2021, we are almost at the end of this cyclicity. So we also have to point it out that this kind of data show trends that are very independent of what I showed before. So before I show variation that are related to the shallow systems of the volcano, Ivan managed to focus and to highlight what change in the deep source that can drive this cyclicity. Why that is important? Because in a volcano like this one, probably are these big waves of recharge from deep magma that can help us to forecast moment of unrest from a petrological point of view. What we can do with texture of or the chemistry is just to say if we have moment of the gassing or moment richer in gas. But this is a real probably I would say petrological monitor that can help, even if the quantification of this ratio takes time because Ivan needs 1 to 3 months to make this analysis, but at the end, these are very, very important. So these data are then made available through the DIMVOLC database. We started with the recent eruption from 2014, but this compilation can go back since the prehistoric eruption at Piton. We just have to find time to fill the table, but Patrick and Andrea have an incredible data set that need to be inserted in this table. So we now wanted to use Aerovolc to have an help to fill this database that then is available to the community. And here we present data from the eruption to the rocks. Here you have images of rocks, of optical images from microscope and the ECM. And here is the list of the data that you can find this database from the sample description that is made by the OVPF to deposit grains as a component for pyroclast, to particle characterization in terms of density, porosity, connectivity, and bulk and glass and crystal chemistry. Texture as well is not considered as a mandatory data monitoring for this kind of approach, because you have to know that we just had recently the Aerovolc meeting in which a work group showed the result from the Aerovolc survey, in which the international community was asked which were the main parameters to deliver during a crisis. So almost all these parameters are mandatory, but not, for example, isotopes or not texture. But I can tell you, although these are not mandatory, as you saw, for example, for the isotope, they are fundamental for Piton de la Fournaise. And in terms of texture, even if they are not mandatory, we start actually to provide them for different kind of lava, from rich olivine lava in 2007, and lava in 2010, 2014, 2015, 2016. So now we start to have a nice data set of texture as well that are quite important, because the quantification of crystal and vesicle and their distribution can inform for the quantification of viscosity then and for the flow modeling. So I end this talk now with the countdown for petrological monitoring. So as I said, Aline and Luciano just sent the samples that were collected by the observatory team, and now we are waiting and start this counting. Thanks.
Thanks so much, Lucia. I was supposed to tell you that it was finished, so it's finished. Thanks very much. If someone have some question for Lucia and Mathieu, it's now. We've got a few minutes left.
I have a little question before Ben. After you can ask your question. Actually, Mathieu, maybe you say it quickly, but maybe it's important to say that the HotVOD platform is also working well on Etna and Iceland and other countries, right?
Right. Yeah.
And which maybe, I don't know, which volcanoes or what would be important?
Yes, actually, Meteosat is geostationary, so you have a field of view centered on Meridian Greenwich and Ecuador, and basically you have volcanoes from Iceland north to Piton de la Fournaise at the south of the Swat, southeast of the Swat, and on the west, extreme west of the Swat, of the field of view, you have the Soufrière de Guadeloupe and Montagne Pelée. So you basically have 50 volcanic targets with varying space resolution depending on the location on the field of view.
Thanks very much. Okay, Benjamin?
Thank you very much for your presentation, Lucia and Mathieu. I have a question for Mathieu about, I don't know much about INSAR, but what is the process to obtain the thickness of the lava flows? What do you need special INSAR data?
I don't think so. I'm not specialist as well. Maybe somebody else can answer your question. But basically, you have two kind of data from INSAR. You have the phase and the amplitude. And I guess for the thickness, you just have to use the amplitude signal of the radar from one image before the eruption to generate like a DEM before, and then another one after the eruption. And then by the difference in elevation model between the two dates, you obtain the thickness of the new and placed lava flow.
Thanks. And I also have a question for Lucia. What is the amount of sample you collect on the field, well, in kilograms or?
Yeah, so it's what they collect. You can ask more to Nico, Aline. Unfortunately, Andrea is not here, but I can tell you, it depends. It can range from 2 to 3 kilos or even more. I say for each sample. And I remember we need to make a distinction between a lava fragment and pyroclast. So, and usually Andrea collect enough, Aline and Nico, because they divide. Yesterday, for example, there was Andrea with a group of people working on pyroclast, and Nicola and Aline working on lava. And so they have to collect enough to send samples in parallel to Clermont, IPGP, and well, I say Clermont, for example, IPGP, you need to have enough to do bulk, all this kind of measurement in section. For the pyroclast, I need to do grain size, componentry. So we need to have enough, and also to keep always a sample at the observatory. So Andrea, when I say storage, is this collection of samples that now is well organized at the observatory. So it's a big effort. And sometimes they have the helicopters, sometimes they do not have it. And yesterday, for example, when they were collecting the pyroclast, they lost a station and they had to run away, but they saved the samples, but they had to run away because the activity became suddenly more energetic and really can be quite dangerous. So thanks a lot, guys.
Thanks for the answer.
Okay. Nicole, you want to ask something?
Yeah, maybe I can comment on how to retrieve lava flow thicknesses from INSAR. My name is Nicole Richter. I was a postdoc at the observatory at Piton de la Fournaise until last year, and I worked with INSAR quite a bit, and the INSAR time series. So in order to retrieve thicknesses, you actually don't use the amplitude, you use the phase information as well. And there is basically two modes. Either the two radar images are acquired at of the same area on the ground, but at slightly different, from a slightly different look angle, but actually at the same time, then you retrieve basically an interference pattern that is related to the spatial separation of the two radar images, and that is related to topography on the ground. So basically, you need separation in space, which we refer to as a baseline of two radar images to be sensitive for topography. And the larger the separation, the more sensitive you're to topography. And then you basically need a second set of these two SAR images after a certain amount of time to retrieve another topographic information map from INSAR. And then the difference of the two gives you the thickness of a lava flow, while the deformation you infer from two radar images that are ideally taken from the same position in space. So the baseline is supposed to be as close as possible, the separation in space, but then you need time to go by for a deformation on the ground to occur, and you get the second image, and this gives you basically the deformation pattern. In reality, you have both components, the topography and the deformation in one interferogram, and you use a external DM to get rid of the topographic pattern that is inside this interferogram because of the separation in space. I hope it makes it a bit more clear. So for topography, you also need, or you also use the phase information, and you need separation in space to be sensitive to topographic features. Yeah, that's it.
Thanks, Nicole. I don't know if there are some question more or if it's okay. Okay, so Oriel, we can close the session. And
okay.
Maybe, okay, we are going to have a good lunch during this rest and coffee for people from far from there. And at what time we have to be there?
So we meet in an hour and a half. So at what time is it? Yes, in an hour and a half at 2:30 here in Europe time. I hope some people can have some sleep for those on the other side of the Atlantic, or breakfast time, yeah, for Benjamin. And yeah, we meet this afternoon to talk a bit more about tracking and modeling effusive eruptions. So I will close the Zoom session now and open it again a bit before 2. For those who will talk this afternoon, please connect a bit before so we can check that your microphone and everything is fine. And that's it. So
thank you very much.
2:30.
Bye-bye and enjoy your rest time.
See you later.